In the last lesson, we talked about paleomagnetism, and we said how it was really kind of proof at last that Harry Hess was right with the seafloor spreading mechanism for moving the seafloor and then the continents. Well, we're going to find that that's not quite exactly right. We're going to need to get to plate tectonics, but really, like I said, Hess was pretty much right for the mechanism. So we're going to do a quick summary here of what we know so far. So what I'm going to do is I'm going to draw what we know. So we have over here, let's say we have a continent. Big continent over here. Over here we have another big continent. In between them, obviously, we have the ocean. So we're going to put the ocean, I'm going to put the ocean here between the two continents. Now we need to get the ocean floor. It's going to be something like this. Remember, it's going to work its way up the mid-ocean ridge here. We're going to have our valley. It's going to kind of go down, slope down, and curve underneath here. Okay, so this I'm going to make like this. What part is this? Well, that's the lithosphere. So we have the lithosphere here. Below it's the asthenosphere. And don't forget we have a core down here with some spikes on it. So there's the core. So we're getting most of our parts. Again, if we want to label the whole thing, this whole thing, I don't know how I can point to it. I'm just going to label the whole thing. That's our mid-ocean ridge. The valley was right there. And what was at the edge of the continents? Those are the trenches. Okay, so we have lots of our information. There's another trench down there. A lot of stuff on here. We also found that it was getting hot in the valleys. So maybe I'm going to get a different color. I'm going to say hot. Okay, so it got colder with depth, but it got hot in the valleys. Okay, why did it get hot in the valleys? Well, because we had convection cells in the asthenosphere. Like this. And they were constantly doing it. So what they did, we said, is it pushed and pulled the seafloor apart. Get a different color. So these are going to push and pull the continents apart. What Harry Hess said was, well, actually, before we get what Harry Hess said, let's add on our stripes. So remember, I'm just going to do them to save time. We had stripes of polarity. So I'm going to do, let's say, normal like this. And I'll do O's for reversed. I'll put 3 on this side and 3 on this side. Okay. Then I'll put some more X's here. Maybe 4 and 4. I'll put 1 reverse and 1 reverse. So we had these symmetrical stripes of magnetism. Okay, the rocks are magnetized. So we have all this stuff going. We have this mirror image idea. It's symmetrical on both sides. The last thing we need to do is kind of finish off what Hess said. He said new ocean floor is created in the valleys, and old is getting recycled in trenches. So this old ocean floor is melting down here and getting dragged into the mantle to be recycled and remelted again. So what we need to do now is we need to prove that it's new here and old here. Okay? That's what we're going to do. To do that, we need a boat. And that boat is the Glomar Challenger. Okay, so in 1968, we had the deep sea drilling project. And their goal was to drill cores in the ocean floor to find age. Because again, we wanted to show new in the valleys, old in the trenches. Did they find that? Yes. So here are the cores that they drew. They drilled thousands of core samples throughout the oceans, and they found that it was newest in the valleys and oldest in the trenches. Okay, so it found three important things. They drilled over 19,000 successful cores. First thing they found was what they expected. It was youngest in the valleys, oldest at the continents. So youngest in the valleys, oldest in the trenches there. They also found that the ages were symmetrical on either side of the valley. Okay? Again, those paleomagnetic stripes didn't just look like they were symmetric, they were symmetric. Okay, the age of them was symmetric. The third thing they found, again, was surprising. They found that the ocean floor wasn't billions of years old like everyone thought. The ocean floor was only about 150 to 180 million years old. Way younger than anyone expected, so it surprised pretty much everybody. They thought it was going to be the oldest rocks on Earth when they brought them up, but it wasn't. Okay, only 180 to 150 million years old. That should make sense because Pangaea, remember, split up about 200 million years ago. So of course they should be younger because remember, what's happening in the trenches? The old rocks getting recycled. So if Pangaea, if these continents were together 200 million years ago, then the oldest rocks should be about that age. So Glomar Challenger found that. So here's a map of what they found. You see the red is the brand new ocean rocks. The dark blue are the oldest. So you see the Mid-Atlantic is the best one to look at. We see the Mid-Atlantic Ridge right in the valley here. The valley is the youngest. As you get farther from the valley, it gets older and older until at the continents you are the oldest. So you see that North America and Africa were the first two to split up. Okay, that was the first split up of Pangaea. That's where the oldest rocks are. But again, it is symmetrical. The stripes on the ocean floor are symmetrical, proving that this mechanism of seafloor spreading was correct. Now, the whole theory or hypothesis of seafloor spreading, there's a little bit of problem with it. We can't just say seafloor and continents. Okay, it's not kind of two separate things always. Sometimes they are, but sometimes the seafloor is welded to the continents. So we have to come up with a different word. And the word we're going to come up with is plates. So we're going to get our final theory, the plate tectonics theory. A guy named Dan McKenzie usually gets credit for developing this in the 1970s. Basically, he took all the information from Wegener, from Hess, from Vine and Matthews, from Coxwell and Dalrymple, everybody, put it all together to come up with this new theory called plate tectonics. So, the Earth's surface, the lithosphere, is broken into pieces called plates. The plates float on the asthenosphere and move because of seafloor spreading. Okay, so we didn't lose seafloor spreading. That's now our mechanism. They either move into each other, so this is the new part, they either move into each other, creating a convergent boundary, away from each other, creating a divergent boundary, or they slide next to each other, creating a transform boundary. Okay. So we have our new theory. Most of the evidence we have already for this new theory. We have all the Wegener stuff about plants and fossils and mountains, all that stuff. We have Hess's stuff. We have paleomagnetism symmetry. We have the Glomar Challenger age stuff. We have so much evidence to prove this. But we really need to prove also that we have plates. We haven't seen that we have plates yet. So what can we use to show that we have plates? We can use earthquakes. So here's a plotting of earthquakes like we've been doing in class on the map. And we see these earthquakes outline big pieces of Earth, big pieces of a lithosphere. Volcanoes, same thing. the volcanoes outline these plates of lithosphere. Tuzo Wilson had another piece of evidence for these plates that are moving, the Hawaiian Islands. The Hawaiian Islands are a chain of islands, as you know. The big island here in the southeast is the newest one. It's brand new, present, right now. You go to the next one, go towards the northwest, we get to Maui, million years old. Get to Molokai, 1.3 to 1.8 million years old. Get to Oahu, 2.2 to 3.3. Kauai, 3.8 to 5.6. As you go to the northwest, the islands get older and older. The Hawaiian Islands are created by a hotspot. We're going to talk about this in the volcano unit. They pop up a series of islands. Then the plate drags that island off the hotspot, so the hotspot pops up a new one. So we have this chain of islands going all the way back to the Midway Islands. They're 27 million years old. And it actually goes farther than that. They get to be underwater islands called seamounts. We have this chain that shows that the Pacific Plate is moving to the northwest. Okay? We have a new island down here it's going to be called Loihi, we think. So a new volcano underwater to the southeast. So more proof that we have these plates that are moving. And here are our plates. You can see there aren't very many. Okay? I can't remember exactly. It was 27, 35, something like that, plates. There aren't going to be very many. Most of them are obvious ones. North American plate has North America and part of the Atlantic Ocean. South America has South America and part of the Atlantic Ocean. African plate, Africa, part of that. So again, we can't say seafloor and continents like Hess and Wegener were saying, because it's not just seafloor and continents, they're together. Okay, this is all one plate. So a plate might have continent and seafloor. There are some like the Pacific Plate, though. It's just a seafloor plate, an ocean plate. Okay? We see all these different plates. You have a map of all these plates. Okay? You're going to need to know the plates on your map. But again, that's easy because they're pretty obvious. North American plate has North America. South American, South America. African, okay, they're all pretty obvious. You can see kind of this picture moving here, showing the map, and then it puts the plate boundaries on. Okay. This map shows the continents with the plate boundaries too. So basically, at these boundaries, that's where lava might come up, that's where earthquakes are, that kind of thing. I want you to add one more plate to your map. The plate that you're going to add is this one here, the Juan de Fuca plate. It's just off the coast of Oregon and Washington. And I want you to add it into your map because it's really important for the United States. That's what causes all those volcanoes in the Cascade Range. Mount St. Helens, Mount Rainier, and it causes all those bad earthquakes that they have up there. So I want you to add that one to your map. So now we finally have our finished theory of plate tectonics. So the last thing we're going to do is we're just going to talk about the different boundaries. And we'll do that on the next lesson.